Hey everybody, this is our lecture on section 3.2, which is on derivatives and integrals. Of vector functions. So, given a vector function in 2 dimensions or 3 dimensions, I'll write it in 3, xt, yt, zt, vector function of one variable, define r prime of t in the way that, we would have been doing this, we would have done it in Calc 1. Limit as h goes to 0, r of t plus h minus r of t over h. So just the same way you would do it with a an ordinary function y equals f of x. So geometrically, r prime of t is going to be a vector tangent. Let me say r prime of a is going to be a vector tangent to the curve r of t at t equal to a. So how do we see that? Suppose this is r of t, right, and we're moving along the curve in this direction. And here is t, and here's t plus h. Let's see, where would be a good place to draw that? Yeah, right here. T, and here's t plus h. So r of t is right here. If this is the origin over here, 0, 0, 0, this is r of t. And this is r of t plus h. And then this is the difference of the two, right there. R of t plus h minus r of t. So as we slide that t plus h, oh, this is t plus h, that's t. Yeah, that's fine. So as we slide r of t plus h closer to r of t, in other words, as we let h goes to 0, what do we see? Well, let's take a smaller value of h. And what do we get? So let's say r of t plus h is here. Now we have this vector. Right, and then as it gets closer, we get a vector that's tangent to the curve. Now, what the length of that tangent vector is, that's a different story that we'll talk about in the next section. So then r prime of t. All right, so there's r of t. R prime of t is tangent to the curve r of t. All right, how does one, so that's the geometric thing, the geometric meaning of r prime of t, just like the, ordinary definition of f prime of x. It's the slope of the curve y equals f of x at that given point. Here, the tangent vector is thought of as slope, right? Because lines are defined with slope vectors. How does one calculate it? Algebraically. Okay, well, it's just simply like this. R prime of t is equal to just x prime of t, y prime of t, z prime of t. Right? In differential notation, we write dr with the vector on top, dt equals dx dt, dy dt, dz dt. Okay, why is this the case? That you just take derivatives component-wise? Well, I mean, you can calculate it. R prime of t is equal to the limit as h goes to 0, r of t plus h minus r of t over h, which is equal to the limit as h goes to 0, 1 over h, and then this is the vector function xt plus h minus xt, yt plus h minus yt, zt plus h minus zt, and then you can use the scalar multiplier here, just bring that inside. That's x of t plus h minus x of t over h, y of t plus h minus y of t over h, and z of t plus h minus z of t over h. And as h goes to 0, this is dx dt, dy dt, dz dt, or x prime of t, just by definition. This is x prime of t as h goes to 0, y prime of t as h goes to 0, and z prime of t as h goes to 0. Okay? Some algebraic properties of the derivative are as follows. One, the derivative with respect to t of r of t plus s of t, if you had two vector functions and you added them, well, I mean, it's just going to be the same as before because you're doing it component by component. It's just going to be the sum of the derivatives because in each component, the derivative of the sum is the sum of the derivatives, and we take the derivative component-wise. Two, the derivative with respect to t of a constant multiple k times vector function r of t is k times the derivative with respect to t of r of t, just like it is with ordinary functions, which is k r prime of t. Three, with the dot product, the derivative of a dot product of two vector functions, interestingly enough, becomes this. It's r prime dot s plus r dot s prime. So you have a product rule. Why is it the case? Right? Again, you take the derivative component-wise. And with the dot product, the derivative of the sum is the sum of the derivatives. The derivative of a sum is the sum of the derivatives, and each term of the sum is the product of the x components, y components, and z components. So for each term, you use the product rule, which looks like that. So it's not, quite as deep as it might seem. But anyway, there it is. We could do the proof, write that out formally. Why don't we do that? For number 4, with cross products, it does the same. Now, proving that's going to take more writing. So we won't actually write that one out. Plus r of t cross s prime of t. And 5, there's a chain rule, the derivative with respect to t of r of g of t is g prime of t is a scalar multiple times r prime of g of t. Let's prove number 3. Okay, we'll just do it for a two-dimensional vector function. Okay, so r of t is equal to xt, yt, and s of t is equal to at, bt. Right? So, the derivative with respect to t of r of t dot s of t is the derivative with respect to t of, now what's the dot product? It's xtat plus ytbt, right? That's the dot product. And now in each term of this sum, we apply the product rule for ordinary real variable functions. X prime t a t plus xt a prime t. Let's go down the line. Plus product rule here, y prime t bt plus y of t b prime of t with ordinary multiplication. But this is x prime y prime, just juggling around the terms. X prime t a t plus y prime t bt plus xt a prime t plus yt b prime t. Right, but this is x prime y prime dot, right, x prime y prime dot a b. So this is r of t, r prime of t, dot s of t. Plus this one is r of t dot s prime of t. Right, which is our desired result. So that's the proof of number 3. The rest are all kind of similar to that. It all comes down to the fact that the analogous property for one-dimensional functions holds. Okay? There's an interesting application of this fact that the product rule works for dot products. Product rule for derivatives of vector functions works on dot products. An interesting property is the following. So suppose that r of t is a vector function for which v of t is equal to k, some constant, for all values of t. Right, that is, v of t is equal to, right, so in 2 dimensions, this is x of t squared plus y of t squared equals k, or v of t is equal to, in 3 dimensions, x of t. Oh, I'm sorry, we're just talking about 3 dimensions here, not 2 dimensions. You can do it in 2 dimensions, but it's less interesting. X of t squared plus y of t squared plus z of t squared is equal to k for all t. That is v of t, or r of t, we've been using, lies on the sphere of radius k, centered at the origin. Alright, so here's the sphere of radius k, centered at the origin of xyz space. So there's y-axis, x-axis, and z-axis, and these are the coordinate k on each axis, and then r of t is somehow on the sphere. Somehow some kind of path that lies on the sphere. So this is r of t. Okay, so if the size or the magnitude of r of t is always the same k, then r of t is some path described on the surface of that sphere. In this case, r of t and r prime of t are always perpendicular. Right? In other words, the radius of the sphere, vector r of t, so the vector whose tail is the origin and whose head is being traced onto this curve, right, like that, r of t. That radius is perpendicular to the tangent, r prime of t. Is perpendicular to the tangent, r prime of t, of the sphere. Right, the derivative is perpendicular to the curve, and therefore it's perpendicular to the whole sphere. And, we know that in general, right, with circles and with spheres, that the radius and a tangent are always perpendicular. So here we get the same thing. Proof? Well, that's one proof right there. The other proof is that, geometrically we know it's true, but we can confirm this with calculus. Okay, so given r of t equal to k, we have that r of t squared is k squared. So, well, the length of r of t squared is r of t dot r of t. So, now, let's take the derivative with respect to t on both sides. Right, here we use the product rule. It's r prime of t dot r of t plus r of t dot r prime of t is equal to, well, the derivative of k squared is 0. K is a constant. It's not 2k. right? It's a constant squared, which is just a constant. So the derivative with respect to t, not k, is 0. But this is, because dot products are commutative, this is just 2 r of t dot r prime of t is equal to 0. So then dividing by 1/2 is equal to 0, and the dot product of two vectors is 0 if and only if the vectors are orthogonal. So which is true if and only if r of t and r prime of t are orthogonal. All right, our desired result. Okay, so that's an interesting consequence, and you know, we can prove that geometrically from known geometric facts, or you know, it just comes right out in the calculus as well. All right. How about some examples of derivatives here? So remember the helix. All right, here's the cylinder of radius whatever. Radius 1, we'll say, in this instance, right? Centered on the z-axis. Right, and then here is the vector function r of t equal to cosine of t, sine of t, t. Right, so, you know, this was an example we had in the previous section. Oops, looks like this. Actually, I didn't draw that too well. Let's give it another go. Got it too steep, I think. So, there we go. Better. All right, so, right, and that lives on the sphere, because, or the cylinder, x squared plus y squared equals 1. It lives on that surface because in this function, x squared plus y squared does equal to 1. The z just tells us how we're moving along that cylinder. All right, so r prime of t is equal to minus sine of t, cosine of t, and then 1. Right, so for example, r prime of at 0, right here at 0, is equal to 0, 1, 1. Right, so it's pointing upward 45 degrees, right, upward and, upward and, you know, to the right. So 0, 1, 1, which is equal to r prime of 0. So that's the tangent at t equal to 0 right there. Different color on that one. A little blue. Right, that's the tangent at that spot right there. What else? Any other interesting examples? The sphere, the helix. Well, let's look at antiderivatives now. Given that given r of t equal to xt, equal to xt, yt, zt, since the derivative r prime of t is obtained by component-wise addition, or component-wise differentiation, the antiderivative should also be calculated component-wise. Right? That is, the antiderivative of xt, yt, zt for a three-dimensional vector function should be antiderivative xt, antiderivative yt, antiderivative zt. Like that. All right. Now, given so, for example, given r prime of t equal to sine t 1, 0, and r of 0 equal to, say, 2 minus 1, 2, find r of t. So we know r prime of t, we're given r prime of t, and we're given r of 0 is 2, negative 1, 2. Okay, so now let's find r of t. Well, r of t is going to be an antiderivative of r prime of t. Right, that's the derivative of r of t. So the antiderivative is going to give you r back, give or take a constant term. And that constant term is going to be a vector term in this case. So this is the antiderivative of sine t 1, 0 dt. So this is equal to, antiderivative of sine is minus cosine t. Antiderivative 1 is t. Antiderivative of 0 is 0 plus your arbitrary constant. But the arbitrary constant, you need an arbitrary constant in the x component, y component, and z component. So your arbitrary constant is a is a vector quantity rather than just a just a scalar term. Okay, so r of t is equal to minus cosine t 0 plus c. So 2 minus 1, 2 is equal to r of 0 is equal to, well, at 0, this is equal to minus 1, 0, 0 plus c. So subtracting this or adding 1, 0, 0 to each side, you have 3 minus 1, 2 is equal to c. So r of t is equal to minus cosine t plus 3, t minus 1, and 2. Right, so similar to problems that we would have done in Calc 1, this is the way we get this answer here. It's just, 3 anti-differentiation problems in one, so essentially. Okay, so that is the end of the lecture on this section.